Welcome to the sixth video on algebraic geometry, where we will plow through a number of problems to get some practice in these new terms and domains. Okay, so we're starting with this problem. We're given a set y, and the set y is just our friendly neighborhood parabola, y equals x squared, in the affine plane. And we need to show that the coordinate ring of y is isomorphic to the polynomial ring in one variable. So how the hell do we do that? Well, we start out by jotting down what we know about this. The coordinate ring, remember, is defined as the ring of polynomials modded out by the ideal of the set of y. We know that the ring we're playing in has two variables, x and y. And we know that the ideal of y is I of z of y minus x squared, right? Because if y minus x squared is sent to 0, then y equals x squared. Bada bing, bada boom. So really, we need to prove that this guy right here is equal to this guy right here, the ring of polynomials in a single variable. How the hell do we do that? And what do we do with this nonsense on the bottom? Well, we have a nice solution about that if we know something from algebra. This guy right here, the ring of polynomials over a field with one variable, is an integral domain. If I have an integral domain that's a quotient of some ring A with an ideal I, then I is prime. And if I is prime, then I of z of I is prime as well and equal to itself, okay, as we saw in an earlier video. So instead of dealing with this mess, if I can just prove that these two things are equal, then I know immediately that I of z of y minus x squared is just the ideal generated by y minus x squared. So in other words, this whole problem boils down to k in x and y, so polynomials in x and y modded by the ideal generated by y minus x squared is isomorphic to polynomials in one variable x. If you've taken any algebra classes before, this should ring first isomorphism theorem to you. Okay, and indeed I've written this down over here. This is a synopsis of the first isomorphism theorem. If I have a homomorphism, a ring homomorphism phi from A to A, and I hit A with it, it's going to give me back A modded by the kernel of phi. So what I want is I want a homomorphism from this ring to this ring. And what do I need the kernel to be? I need it to be this ideal right here. So I need this homomorphism, and I want this to be the ideal. I want this to be the kernel. Remember what I said about imagining the ideal as basically, quotienting out by an ideal as shoving everything in that ideal to 0. That's precisely what I need here. So what I want this to become is y equals x squared. That's just by setting y minus x squared equal to 0. If I do that, what I'm essentially doing is I'm sending everything that has a y in it to x squared. I'm sorry, I said that imprecisely. Every y I find to x squared. I'm replacing y's with x squareds. And so this gives me a good idea of what my homomorphism will be. The homomorphism will be p of x and x squared. This is clearly a homomorphism because suppose that I multiplied p of xy by q of xy. Then I would have on the other side p of xx squared, q of xx squared. Wouldn't have a problem with that. Again, it's very simple. I'm just replacing y's with x squared. So this is a homomorphism. And now we ask ourselves, is the kernel equal to this ideal? Well, one direction is obvious. Remember, I have to prove two directions, inclusion from one direction and inclusion from the other direction. This is obvious, okay? I'm aiming this way. That's why this is backwards and this is forwards. If I plugged in x squared where I saw this y, it's going to give me 0, right? So this inclusion is very obvious. So that leaves me with this inclusion, which is not quite as obvious. We have to pick an element of the kernel and show that it's in this ideal. So here's a generic element of A, the ring of polynomials over K in two variables x and y, and I'm assuming that it's in the kernel. For this, I use a trick. I can think of polynomials in two variables x and y as polynomials in one variable y with coefficients in the ring of polynomials in one variable x. So I can think of polynomials in two variables x and y as looking kind of like this, with some y to the i's up here and then some q sub I of x. These are just polynomials in the ring of one variable x. Further, since I've assumed that that P is in the kernel of phi, that P is in the kernel of phi, then phi of P of xy, which is just this, I take the y's and replace them with x squareds, this sum is going to be equal to 0. I'm now going to do something rude and draw a line up here so that I have more space. So one thing I can write here is that P of x minus 0, which is just P of xy minus phi of P of xy, since P of xy is in the kernel of phi, it goes to 0. And then I can rewrite using these definitions. And I get something that looks like this. Now, if we think about this for a second, this is very clearly divisible by y minus x squared. Therefore, we have that the polynomial in x and y, if it's a member of the kernel, is also a member of this ideal. So we have the other direction, and we have equality. Here's the second part. Should probably do this. That was the first part of problem 1. This is the second part. We have a set z. Z is the hyperbola xy equals 1. And we need to show that AZ, again, the coordinate ring, is not isomorphic to the ring of polynomials in one variable. This amounts to showing that this quotient here, which is our coordinate ring, is not, for some reason, is not isomorphic to k of x. So we need to find a compelling reason. Remember that when we are modding out by an ideal, it's the same as sending everything in the ideal to 0, sort of. In other words, I want to send all xy pairs to, not all xy pairs, but all xy products to 1, which is the same thing as saying that x is kind of like 1 over y, or y is kind of like 1 over x. Now the reality is, I could take every y and plug in 1 over x, and I would wind up with some ring that had a bunch of x's in it. However, what this right here is saying, what my constraint given by the ideal is saying, is that x and y are not just together in a ring or replaceable, they are in fact multiplicative inverses. What's true about this polynomial ring is that it only has invertible elements in the base field k. In other words, let's try to find an inverse for the element x. Well, we can't do it, right? If this were, let's say, the ring of formal power series, maybe we could find an inverse for some certain elements that also had non-zero constants, but this ring does not have general invertible elements, so these two things cannot be isomorphic. Before moving on, it is true that this coordinate ring is isomorphic to the localization of the polynomial ring of x at x. The third part of this problem is possibly the most involved. Given irreducible quadratic in two variables, f, let w be the conic defined by f, and show when the coordinate ring of w is isomorphic to the coordinate ring that we discussed for y, that's y minus x squared, and when aw, the coordinate ring for w, is isomorphic to xy minus 1, or the coordinate ring for the set generated by xy minus 1. So I've written out here a form, the general form of a quadratic in kxy. Now, some of you who've seen videos up to this point might be asking yourselves, why in God's name are we playing in the affine space? What's so special about the affine space? Why can't we play in Rn? Why can't we play in Cn? Why not? This is why you're about to see. I'm going to be able to basically attack either x or y with any linear transformation that's non-singular. And I'm going to use that profusely over the next few minutes. The beginning of this problem is dividing it up into cases. I start with the case where both a and c are 0, so this is just barely a quadratic and only with this annoying xy term. So this is the general form of a quadratic like that. What I do first is divide off b so that it doesn't screw up the rest of the equations. And I have this nice clean unitary, or I shouldn't say unitary, that actually means something. I have a 1 for a coefficient for this term. I've now factored out an x from these two terms right here. I'm now going to send y to y minus d prime. This is just a linear transformation. I've now gone ahead and simplified this. So basically I've plugged in y minus d prime everywhere I saw a y. That took care of this plus d prime. Now I've got xy, and then I had to factor through, and I just simplified this constant term to f prime prime. I'm now going to factor out a y from these two terms. And I'm now going to make my final linear transformation of x, where I send x to f prime prime x minus e prime. I now divide through by f prime prime, and I'm left with my final product. So this demonstrates that when a and c are 0, this quadratic gives me a coordinate ring that is isomorphic to the coordinate ring for the hyperbola. What's about to happen is something completely wacko. I did not come up with the solution, though I am going to go more in depth on why it works. But if you just saw this solution, you would be tempted to drop this topic immediately and feel like a moron for the rest of your life. This has to do with these kinds of transformations that you do in this sort of, if you want to break these things down. So we begin by assuming that a is not 0. Really, we just need one of either a or c to not be 0, and they kind of tend to the same answer. So we're going to assume that a is non-zero. And in fact, we're going to go ahead and assume that a equals 1 to sort of get it out of the way. We now have this somewhat less hideous beast. We're going to do something now which again may seem completely out of left field. So what I'd like to do is kind of go over to the side here and explain why we're about to do what we're about to do. The whole idea is we have this pain in the ass term right here that we need to do something with. It would also help if I could kill off one of these terms or these terms. You'll see why in a second it makes so much sense to remove one of these, but for now, take it by faith that removing this term right here is a good idea. So the goal is we'd like to kill off b if possible, and we'd like to kill off one of d or e as possible. We'll choose d. So our choices of transformations for x are basically linear transformations along with translations into something that looks kind of like this. And again, we're looking at some form that looks like this. So here I've gone ahead and drawn what these transformations on each, or the transformation of x would look like passed through the entire polynomial. And again, what I want to do is kill off b and d. So I begin to hunt for all examples of something times xy in here. And that's going to help me figure out what k and l need to be to kill off b. There's only 3 examples of xy in here. There's 2 k xy's up here, and there's 1 bxy down here. So I'm going to need 2k to be the opposite of b, or in other words, 2k minus b to equal 0. Next, I want to do the same thing with d. So d was the coefficient of x here, so I'm going to want to find every example of x and try to balance them out as well. I've gone ahead and put a box around every x that I could find, and I have only 3 of them. Here I have 2 of L times x and 1 of D times x, and I need 2L minus D to be 0. In other words, I need minus D over 2 to equal L. Now I just need to fill these in, and I'll have the correct transformation. So this is what I want to send x to in order to kill off both b and d. Now, I've gone and done this transformation. Notice that this is probably going to affect all the coefficients that are left, but I know that I've killed off b and I've killed off d, and I now have this much simpler polynomial that I can play with easily. This next part comes with dicking around with this for a while. There are actually two additional cases I have to consider, one when c prime is 0 and one when c prime is not 0. First, we'll tackle the case where c prime is 0. We send, oh, hang on, that's wrong. There we go. We send y to y over e prime minus f over e prime. I now realize that I did something backwards. What I'm going to do is reverse the signs here, and that's going to fix my problem. I now have x squared minus y equals 0. Again, when c prime is not 0, I have this right here. I can also conclude from this that, well, actually, let's just move forward. Here we go. So I'm looking at this here now, and I see that I can write this as x minus the square root of c prime, y, x plus the square root of c prime, y. And again, I don't remember if I've mentioned this or not. I definitely should have. I'm working in an algebraically closed field, so I don't have to worry about whether or not the square root of c prime is in the field. I then apply these transformations in order. So obviously the first transformation left us here. The second transformation left us here. And this, as you'll note, is the same as the first type of polynomial, the first type of quadratic that we ran through. So we know that in the case when c prime does not equal 0, we have xy minus 1 equals 0. We can transform it into this. Again, some of these transformations, especially, this one, I think, kind of seem odd, right? And this, I think, comes out of practice and comes out of kind of strategizing about what you want to do with these coefficients, then going off to the side and figuring out how you can accomplish that. I certainly didn't come up with this, and I guarantee you the guy who I saw this from didn't come up with it either. So don't freak out if this seems totally freaking arbitrary to you. Just strategize a little bit and attack the problem.